Alright, should be making a video and such. A little later than usual, so we'll see what that does. See what kind of change it makes in the performance of the video. However, to state that, anyway. Alright, preliminary crapola, and then we'll be dealing with this video. It should be visible if I get rid of this chat thing. We put that behind it, I guess, and then it's not in the way. Well, it didn't work. Huh. Okay, let me try again. Oh, that did work. Alright, so conservation of energy explained, and it's not a very good explanation, so that's why I guess I'm going to pick on it, sort of. That's what you do, is you see something and just ain't quite right. And so it's a very nice contraption he built. So just for the sake of showing another experiment, there should be a lot more of these in the visible universe, the watchable. I don't know why he reanimated it with the, well, he had to fake it up, I guess, to make it look more interesting, you know, more than it is. But anyway.
Hi, and welcome to High School Physics.
Alright, that's way too low. That should be up there, and this should be there, about there, I think.
It's explained. Today I'm going to demonstrate something with this ramp that I made a week or so ago, and you can see that I've made actually 3 ramps, all with slightly different inclinations, a red one, a white one, and a blue one. And you'll also notice that they all
And you got all this merchy crap behind you, which is really tacky.
start off at the same height and end at the same height. And I'm going to roll 3 metal balls from the end of the ramp. I'm going to ask you the questions. Number 1, which one will arrive first, second, and then last?
Right, so he's got them in the right. Oh, what the fuck is going on with all this extra crap? Frankly, yeah, I watched it on Bling and there's no ads. So yeah, if you use Bling to watch YouTube videos, they take the ads out. Kind of funny. Anyway, yeah, so it's, you know, obviously this will be the fastest because it spends the most time at the highest velocity, and this will be the second, and this will be the last in terms of which one will take the longest. And it's just about how long you're in the gravity thing times the friction, blah, blah, blah. The amount of time you're, and that's, friction's the wrong word, how quickly you get up to the maximum velocity. It's all that matters.
And which one will leave at the greatest velocity? So let's see and find out.
So there's the first one, is all the way down here. So obviously getting up to speed quickly, and then you maintain your speed and you're way ahead in the race. And this one's here, and look at the little red one, is barely even going anywhere, and he won't pick up his velocity till the very end, so he'll be way behind. But it's a really good illustration of the fact that you're going to keep these things in the gravity. You're extending the period of time it takes them to acquire their gravitational potential. And the thing is if you, obviously if you weighed how long these things had weight on them, you could figure out that, well, the one that the marble leaves the quickest means, you know, obviously it has the less friction, the less weight was on it for the less period of time. And that's really where the gravitational potential energy is going. So even though it's 9.8 meters per second, okay, and they're all going to be in the gravity a different amount of time, they're only going to take all the rest of their, all the delay is just a way of absorbing the energy through friction. And so you're just changing how much time it takes for them to free fall. So you're just extending the free fall time, delaying it, okay, by holding the object up against the gravity, essentially. And the last one.
Well, did you expect that? The blue one arrived first, then the white, and then the red.
I did expect it because, yes, I've been immersed in this subject for years now. Yeah.
But did you notice they all had the same range? That means that they all left at exactly the same velocity. So why is that? Well, today we're going to answer those questions and discuss the law of conservation of energy. So stay tuned.
So it's not going to be done very well in a sense, because the obvious correct answer for why there's a... Well, we'll play it out.
So here I have a diagram of our setup, and before we talk about the law of conservation of energy, we just need to quickly look at the physics just in terms of the experiment. So here I have my metal ball and I place it on top of the ramp, and the ball of course rolls down the ramp and then off the ramp with a certain velocity and then lands at a certain displacement away from the tabletop. Let's break that down. Well, the first thing I do is I raise the ball up. So in other words, I'm doing work to the ball.
No, okay. So you're not doing work to the ball, okay? You're doing work against gravity. So first off, I mean, this whole way they describe this stuff is this thing having the potential when, again, this is like a boat on the side of a shore of a river. Until you release it into the river, it doesn't have nothing, okay? And so to me, it's just a wrong analogy to say somehow the boat has potential energy when it's sitting on the shore, when no, it's just a boat, okay? And it's not until you put it in the river, you let it flow down the river, that it has anything, that it can gain anything. And it gains it based on how long it's getting hit by the river and how much you allow it to proceed. So if you tie an anchor to it and you drag it along, okay, it's going to take it a while to gain speed.
So that work, in this case, causes a change in potential energy. So my work done on my ball is equal to the delta U, my change in
Yeah, whatever. Potential energy is just to kind of, again, these are physicists, I call it baby talk. I mean, it's just stupid to call it potential energy. There's only one kind of energy, it's real energy. And all you're doing is saying, can I tap a source of energy? Is a spring compressed? Well, it's in a state where, yes, it can, give back the pressure that was used to compress it. So it's been stored. The pressure has been stored in the object. It's not just some kind of potential thing. It's not a different kind of energy. It's the same kind of energy that exists when you push two magnets together. You don't think there's a non-active force repelling the magnets.
Potential energy, and that is equal to mgh. And
Jeez, it's always something. Sorry about that. The trolls, the attackers, they have to crank call me. And so I usually have the phone disconnected, and but because I made the video at a different time, it didn't work out.
my h in this case is the height that I raise it at. And in this case, the height ends up being 24 centimeters.
Right. Now, I've complained before that the MGH is just the wrong way to think about it. The H is it's an illusion, frankly, 4 times the distance, twice the velocity kind of argument, and that MGT is the correct way to analyze it. And in this case, they'll give you the same answer. Okay, if you use 1/2 mv squared and use MGH, you'll get an answer for the speed, for the time, all that stuff. And if you use MGT without 1/2 mv squared, you also get the same answer. So momentum gets the right answer, gets the same answer because you're not fooled by the height thing, the fake height.
Now the ball loses that potential energy. The gravitational field is doing the work now, and so what we have is a drop in potential energy, but the outcome is we end up getting a gain in kinetic energy. Now regardless of the path of...
So just more, frankly, it's just stupid. Obviously you're holding it up against friction. You're not allowing it to free fall. and there's a certain percentage of the free fall that you've deflected, okay, that you've stopped. So essentially you just think of it as banging into this surface and constantly being prevented from gaining its maximum velocity.
The ball, they all end up leaving at the same velocity. Now, how do I know that? Well, I determined the velocity by using simple projectile motion analysis. They all landed at roughly the same position.
So their real velocity, okay, is going to be both vectors. So they have a velocity going down, and they also have a velocity going sideways. So he's just talking about measuring the one velocity, that is their horizontal velocity. He's not counting their vertical velocity, which obviously will increase because they're falling in gravity.
Now, the blue ball and the white ball landed at 57 and 58 centimeters. The red ball was slightly different, but it's roughly the...
So this experiment, again, is the one, Brozo attempted to prove something with when you can't, it sort of proved just how fallible he is in terms of how he does experiments, because this is a law you can't change. I mean, if you get this velocity at right here at this point, you can't evade the fact that the two forces act independent of each other, and you're really not going to absorb any of the energy. It's not a measure of how much energy it has to measure how far it travels, because what's deciding how long it's going to be allowed to travel is the fact that the ball is going to fall at the same rate no matter its mass. So they're all going to end up in the same location because the time is the one dictating if they have the same velocity. So a half mass is going to do exactly the same thing as a full mass in this case. Can't do much about it unless you change the velocities.
The same, and so because they traveled under projectile motion, I can work out the velocity at which they leave. Now, I'm not going to do the calculations here, but
so again, he didn't really calculate this path velocity. He calculated the one velocity. The fact is that it has both. So you have to draw the vector going this way and the vector going this way, and then you have to do the hypotenuse, through the center of that square, that rectangle, to find out the actual velocity when it hit the ground, because it has both components.
Calculations ends up being around 1.36 meters per second. So in other words, the balls all had the same mass, they all left at the same velocity, so they all had the same kinetic energy.
Yeah, so again, they all had the same momentum, but regardless, yes. But the funny part is if you just calculate the free fall, okay, so if you calculate how much speed it should have at free fall, that number isn't going to match this number.
In fact, they have the same change in kinetic energy because the kinetic energy at the top of the ramp is 0. So my delta K is equal to a half mv squared, and this is of course the same for all three balls. They all...
Right, so you don't need this at all to get these numbers. So this number is calculated without it, frankly, and so it doesn't mean anything.
All ended up having the same loss of potential energy, and they all ended up having the same gain in kinetic energy. What does that mean? Well,
it doesn't mean anything because there's no potential energy, and they all fell. Gravity provided the energy for all three, and they all fell the same distance, and all you did was change how long it took them to fall that same distance. But that's all there was, and that would be the extra friction that was absorbed by the different tracks. So the different tracks absorbed different amounts of weight and pressure for the equal to the extra amount of time it took them to fall the distance.
That means that if I have my total potential energy at the beginning,
just checking. Yeah, I gotta make sure everything still works.
And my total kinetic energy at the beginning, and we'll call this naught, that ended up being the same total potential energy at the end plus my total kinetic energy at the end. So in other words, the total energy that they had at the beginning is equal to the total energy they had at the end.
Which is 0. So what's the point? Because he pretends it doesn't, it's not moving, therefore it doesn't it's not going to be it's not going to do something to change the energy, when of course it's going to fall in gravity, so it's going to do a lot of things.
And that's the concept of the law of conservation of energy. Let's explore that a little closer by using this great animation.
All right, so I would say the real concept is, understanding that motion and mass is all there is, and it's just mass is moving. If it's a lot of mass and it's moving, it means it's a lot of energy. If it's a little bit of mass and it's moving fast, it's still, because it's a small mass, it's not very much energy. So I'm not going to bother with this. This is just, a roller skater going down, up and down a loop. It's just useless, trivial, almost superficial. All right. So let's get to the more
energy transformed, but you neither gain energy or lose energy. And that's the law of conservation.
So you're not gaining or losing anything. You're being pushed by something, and then you're fighting against the push. Quite simply, you're going downstream, then you're going upstream.
Conservation of energy. Can we now verify the conservation of energy by actually predicting the velocity at which these balls should go off the ramp?
So he's going to predict the velocity. What he's really going to do is calculate the free fall velocity. So technically it should be the same. This dropping the ball straight down should be the same as doing all this crap. But you got to take into account for the fact that these things aren't being allowed to free fall. And their end condition is going to be different than this one's end condition. So if I just drop a ball, I might as well say the big key word, it has no angular momentum. It's not going to be spinning. It's not going to be rotating. So if I just drop a ball, it's not going to be rotating when it gets here. All three of these are obviously rotating when they fly off the edge. So it's obviously the angular momentum is where there's all the energy that's missing is stored. So the reason why it doesn't have the same velocity when it reaches the final drop in distance is because, in a sense, although these are pretty frictionless tracks, they're still causing the motion is dependent on forcing the steel balls to have angular momentum, rotation, and the rotation is what's stealing a big piece of the energy. If they were very light, then they would steal less. If they're very heavy, it steals more.
Well, we know that the total energy remains the same. So in other words, the initial potential energy plus the initial kinetic energy must equal to the final potential energy plus the final kinetic energy. Now we know that our initial energy was equal just to mgh. We had no kinetic energy.
So we could just do the same equation with just doing momentum. Okay. Initial velocity, final velocity is all it really comes down to. And instead of mgh, it's mgt. So if we use mgt and just measure how much time it takes for this to drop the 24 centimeters, which is something like 16th of a second, you'll end up with the same answer. And it's not this answer, it's the free fall answer.
On the other side, we only had kinetic energy. There was no more potential energy, at least relative to the table. So I get a half mv squared on that side. Now, do you notice what happens? M is constant.
So I'm just saying you can kill the h and put a t here, and then kill the half and kill the square, and you'll get the same answer. So I'm just saying, just to understand, you don't need to do this formalization. You can just do mgt and forget about this kinetic energy formula, because it will equal mv.
So in other words, we can cancel out the m's. And what does that mean? Well, it basically means in an ideal situation that this setup of conservation of energy is independent of the mass. In other words, the velocity of the ball in this case is going to be the same regardless of what mass you have. So we have 9.8 as our acceleration.
So that would be true if you weren't rolling them down the ramp. So if you weren't rolling them, the mass is now quite significant, because now the rotation is you're rotating a lot of mass, and so the heavier they are, the slower they're actually going to be flying off compared to the free fall height, because you'll have more and more energy stored in the rotation. See, when these fly off the end, you can just understand they're still spinning. They're still rotating. And that's a big difference between the one just free falling, no rotation. So the one free falling, no rotation. The one's coming off the ramp, rotating.
Relation due to gravity, we multiply it by the height, which is equal to 0.24. That is equal to a half v squared. Now, if I calculate v out from this situation, I'm going to get a value of 2.16 meters per second.
There. Now you'll get the same. I don't know what this stupid shit thing he got in here is blocking his own screen. I didn't do it. It's not my fault. Anyway, I don't know what the fuck that is. Anyway, you get the same number if you use MGT. So if you use MGT, you get the same calculated number for how fast it's going to be going in free fall, falling. So this is a free fall math. It isn't a down a ramp math. And now he's just going to say the magic word.
That should be the velocity of the ball that goes off the ramp. But hold on here. I've got a value of 1.36 meters per second. Why is that?
So it's not an insignificant difference, right? You're talking about whatever 60% or 40% of, yeah, for, let's see, 70 would be 60. 60 would be almost a third of the energy.
Well, that's because if you listened to the experiment, the total energy that I had put in the system wasn't just being converted to kinetic energy. There was also energy being released in terms of heat and sound.
All right, and we know that the one that took the longer path made more noise and it made more friction with the surface. So the one that took the longest, and yet it came out the same speed. So the friction doesn't seem to be have anything to do with it. The friction seems to be something gravity takes care of. In a sense, the longer you're in the gravity, the more the energy goes into friction, and your final velocity will be very close to your free fall velocity. But that didn't happen, and it's because of the rotation is what absorbed it. The rotation is what ate up this difference.
And so we need to allow for that as well. In other words, the situation isn't ideal. Let me explore it again by looking.
So we're going to skip that part again because it's just too boring and stupid. So he's just talking about friction. So he's using this stupid skater example. So he uses this stupid thing and all he does is slow him down. He creates some drag and he calls that heat and has a little bar going up and down. It doesn't mean a damn thing and it's just trivial and silly. Here, I'll just play some of it so you can see. This is what they do. They do this fake kinetic potential crap. And then he throws thermal in here. And I don't know what this one is. You can't even read it, but whatever. Total, he says.
Skater doesn't end up going as fast. In other words, the kinetic...
I mean, obviously the total energy should be diminishing, and he doesn't even do that correctly. I mean, obviously the total energy in the system is decreasing as the thermal energy escapes. Obviously.
Energy lowers. The potential energy lowers because we're now losing some energy in terms of thermal energy. Now we haven't lost.
So, and again, it just calls it thermal when obviously it's not just thermal. It's all kinds of sparks and things, pieces of the grit moving and little pieces breaking off and all kinds of different ways the friction steals the energy. But in the case of the experiment he did, friction isn't the cause. I mean, you could make the ramp out of rough wood, and you could do lots of things to change the experiment, and frankly, it's the rotation that's going to steal all the extra energy.
So it's just been transformed into a form that we can't utilize, and so as a result, we have our
So we'll see if there's, there's some chatters chatting, so let's see. Gus, wow. What if you're misunderstanding everything you're being told? I don't know who you're saying that to. That's my whole point. You don't know the history. You don't know who Leibniz was. You don't know who Madame Châtelet was. You don't know who she was tutored by. And frankly, you don't realize there's only 2 fucking experiments in the history of science, okay, defending kinetic energy. Okay, that's it. Dropping round things into clay and some bogus air track experiment where you make free momentum. And that's all you've got on your side. You don't have any evidence in 350 years of it ever taking 4 times the fuel to move anything twice as fast. What if I told you you're not making rational arguments? Well, then you can go fuck yourself. because they're not arguments you can counter with anything, you fucking lame piece of shit. So let's just read these out. What if you never were MIT material? What then, Gary? Well, the fact was I was accepted tentatively by MIT. All right, they invited me to come be interviewed. Okay, they don't invite you to be interviewed if there's, no chance. Yeah. Gus, how stupid one can be commenting 10 years after hard work that produces answers. So how shit clueless off topic. Yes, all that is true. At Gus, why don't you counter his arguments if you think they might not be rational? Well, I'm just saying they're clearly rational arguments. The point is whether they're significant. You people seem to believe that there can be such a thing as momentum in the universe, whatever the fuck that even means, and this kinetic energy stuff, and they don't have to get the same answer, and they can say something has different amounts of energy, right? Momentum says the bullet has the same energy as the gun recoil. Kinetic energy says that the bullet has 1,000 times more energy. Put that into space. Is it a rational question to ask? What happens in space? If I have a spaceship and I shoot a bullet, okay, 2,000 joules out one side, and I just do the recoil of the gun out the other side, 2 joules. Does my spaceship turn? Now, it's perfectly rational to ask a question and expect you to answer the question. What is your guess? Does the spaceship turn? And if you say it turns because you believe in kinetic energy, then I'm going to laugh at you and say, well, NASA doesn't think so, retard. Okay, I see a lot of people say draft science is irrational with an explanation as to why he would be. Well, I just point out exactly what the fuck is irrational, the sentences, and all they can do is quote mine and find something I said inarticulately. Which reminds me, when I drew the perpetual motion machine, I did have the lever turned the wrong way. The fulcrum was in the wrong direction. So, yeah, I do make mistakes, but they're trivial and not very important. I'm not for any side. Well, you really should be by now, frankly, okay? So if you're not for the side of evidence, then you're still an asshole, right? I'm for the side where you have evidence before you claim something to be absolutely true. So if they're going to tell you there's 1/2 mv squared energy in the universe, you ought to say, well, show me it taking 4 times the fuel to go twice as fast, okay? Just show me and then it's all resolved and we're done. Show me that levers don't conserve momentum. Show me that if I can, I put the 2 mass 1 unit of distance from the fulcrum and the 1 mass only leaves with 1.4 the velocity. It doesn't leave with twice. Show me. And then we're done. Einstein don't even want to touch the argument. Yeah, they don't want to touch, and you don't want to touch the argument that shouldn't you be convinced by evidence? Credible evidence. I mean, the evidence that it's not easy to debunk, like the dropping round things into clay, where I can just keep arguing that, well, stop dropping round things and see what happens. I'm on the side of truth. Well, again, you should be on the side of evidence. Voltage is measured in joules. Voltages? Well, sorry, no it isn't. Wattages, you retard. Therefore, doubling the voltage doesn't double the velocity. I don't know why you're on this subject, but says you, frankly. I don't think you understand how electricity moves through wires. I think it obviously is exactly that. The voltage is actually increasing the speed with which the electrons are communicating with each other, the pressure with which they're moving, the velocity of the electrons. Voltage is the velocity of the electrons. Yeah, let me go ahead and counter all his nonsense in a 200-character chat comment. Well, you can post it anywhere you want, but the point is you're not doing anything useful in the chat then, are you? You're just going to say, fuck you, and say, there, I've made my counter argument. So if that's all you're going to do, then I'm just going to block you, right? You can't, if you can't make an argument, you can't put it in the comment section, you can't manage the task, then you have nothing useful to do here, right? Other people seem to be able to ask questions or to state, things on the topic in the chat, so they're able to handle it under the 200-character limit. So if you can't do it, then just say you're incompetent and you can't participate. Maybe I already did that in my videos, and maybe others have too. You have videos? Well, this ought to be pretty funny, frankly. So let's go find this. Let's see. Go to channel. Let's see what it does. Let's see. Oh, no, we don't have anything, Gus. Yeah, so we don't have any videos from Gus. Alright, so that didn't work at all, Gus. Yeah, frankly, so I don't understand you, Gus. Sorry, I don't get you. I guess I could probably move. Well, I don't need to bother. I'll get back to the video. Maybe I already did that in my videos. I don't understand what you're talking. You have no videos, and maybe others have too. So where's your videos? I shouldn't have said I'm not on any side because I don't see how kinetic energy makes sense. Thank you. Until they show me it making sense, I don't have any obligation to think it makes sense. I mean, frankly, it just sounds pretty stupid that it's 4 times harder to press a spring twice as much. If it only takes twice the weight, how could it be 4 times harder? Is twice the weight 4 times the harder to produce? I don't think it is. I mean, I lift something, you know, this weighs a certain amount. I lift it up. Okay, that took a certain amount of energy. I lift 2 of them up. Well, that's twice as much work. It's not 4 times as much work. I can figure that out all on my own. So your theory sounds pretty silly to say it takes 4 times the energy to produce twice the weight. Doesn't make any sense at all. I mean, how do you make that make sense? I'm just saying, how does twice the weight take 4 times the energy to produce? But that's exactly what happens in gravitational fall, right? I drop the object from 4 times the height. It only weighs twice as much. Let's see. This seems like the easiest thing to disprove with basic experiments. Why hasn't it been done? Obviously, because it would prove it's crap. That's why it hasn't been done. Of course, they keep evading it because, damn, it's not going to work. The experiment won't validate the theory. So, of course, they haven't done the experiment. Because if they do the experiment, it'll overtly show it's all bullshit. So, if they actually measure how much gasoline it takes to go 30 miles an hour and then how much gasoline it takes to go 60 miles an hour, the answer will be, fuck, our theory is shit. That's going to be the answer. If they actually measured how much work a bullet can do versus how much work, okay, how much electricity, let's say, we could put little generators on them, figure out some way to collect the energy from the bullet and collect the energy from the recoiling gun, they're going to find out that the bullet doesn't have 2,000 joules of energy and the gun only has 2. They're going to find out that the answer is a lot closer to be, 50-50. The bullet's probably going to have more just because, yes, it probably acquired some extra velocity because the gun didn't move and the explosion actually moved a little bit forward in the gun. But it's not going to be anywhere near 2,000 to 1. It's not going to be 1,000 to 1. It's going to be much closer to 3 to 1. Big difference between 1,000 to 1 and 3 to 1. Big difference. Alright, so I'll go back to the video.
Increase in potential and kinetic, but the total energy is still the same.
So, it's kind of silly to say the total energy is still the same when we know the heat energy is dissipating probably quite rapidly and we're not going to be able to store it and do anything with it. So that's kind of, the system is losing that energy.
The law of conservation of energy is still true. So, why did they all leave?
So obviously I believe in the law of conservation of energy, but you're only conserving momentum because there is no other energy. There's just masses, moving velocities, and that's all the energy that ever happens in the universe, and it just exchanges between objects. One object has momentum and it can give it to some other object. And that's it.
At differing times. Now, in our 3 ramps, they all have differing times because of the different accelerations that are occurring along each of their paths.
So obviously it's when they accelerate. So this one accelerates quickly, so most of the distance it travels at a high velocity. This one travels most of the distance at a very low velocity, and this one's right in between. It's just showing that you can lift something slowly, you can lift something quickly, blah, 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 blah. And obviously, if you wanted to collect more energy, you would collect more in terms of weight from the red one, even though, so it took longer But if you wanted to get that energy, you could collect it as being pressure. It applied pressure, gravitational pressure, to the table longer than the other two did. Thereby, it put more energy into the floor, you could argue. The red one, there was more energy that went into the ground than with the white one or the blue one.
They all start off with an initial velocity of 0, and they all end up with a velocity of v at the end, but the accelerations are different. In terms of the white ramp's acceleration is relatively constant, and I'm going to just call this a.
So it has nothing to do with the constancy of the acceleration, right? This one did it at the last minute, this one did it the first minute, huge difference. So it wasn't the same. It's not the pitch of this or any of this pitch argument. It has nothing to do with it. It's when, okay, you accomplish the task of maximizing the speed. So the faster you gain the full speed, the faster you travel the distance. You know, yes, it takes, you'll get there first.
Where I have here, I have a first acceleration, and that's actually a really small acceleration, and this is a slightly larger acceleration over here. With the blue ramp, we have a relatively high acceleration here, and then practically no acceleration here.
And so he's also got to include that he also has another acceleration here when he changes the direction. So he ends up with a velocity going in the down direction that's pretty substantial. He has to convert all of that into the horizontal velocity.
The bottom, assuming it has a constant velocity. That means the time it takes for each of these things will be different. So in other words, the time here is going to be relatively large, and here the time is going to be relatively smaller as a result. With my acceleration in between, I'm going to have a time that is a set time, and in this case this time is going to be somewhere in between the sum of those two times. And then with my blue ramp, I'm going to have a very small time over here, but depending on the length of my base here, I'm going to get a...
Right, so look, I'm just arguing. I think this is a kind of a rubbish way to explain it. I mean, obviously all you're saying is you have a distance to travel, you want to spend the most time possible traveling it at the highest velocity. So the sooner you get it going sideways, the faster you're going to get to the end target. And the slower the longer you take to get it going fast, where you grab the energy from gravity. So this one grabbed all the energy from gravity very quickly, high velocity, very quick. And that's all there is.
Roughly larger time across here. Now, in our case, the sum of the times for each of the ramps results in the fact that the blue one is first, the white one is second, and the red one is third. So does that mean my blue path is the fastest optimal path in any situation? Well, the answer is no. Let me give you an example.
So I think it is actually optimal, frankly. So straight down with a little tiny curve at the end would be optimal. So blah blah blah. But yes, the less time you're spending. I thought there was. I guess I must have skipped over it. Let's see. There's a whole problem where he had these velocities don't match. Okay, so maybe it's the end here where he points that out. Okay, so we have to go back a little. So he gets a velocity here and a velocity to this equation. Those two numbers aren't going to
squared.
match.
Now, if I calculate v out from this situation, I'm going to get a value of 2.16 meters.
Right, so I played that part. Okay, so yeah, he didn't say anything more on it. So you notice that. So he didn't say anything more. He just did a friction argument, and it said friction, we're supposed to just deduce that somehow friction stole the energy, and that's why there's this huge difference between these velocities, the calculated velocity, what it should have been, and what it actually is. And I would argue that what he's missing is the angular rotation is what really stole the energy. So the extra energy is in the fact that this is rotating. This one, free fall, wouldn't be rotating. All right, so but he just ignored that whole subject. All right, let's get through this. Sorry, now I've lost where I was.
Let me give you an example. Let's say I have a fourth track, and I didn't build this because it was a bit difficult for me to make this. So let's draw my path down like so, really quickly, and then it ends up being flat all the way to the end. That means I'm going to get a relatively short time here because the acceleration is actually really high. But my time across the bottom section is going to be relatively large. Why? It's already traveling at its maximum velocity, which is the same as the blue path, but it's now traveling much further. And so therefore, as a result, its time here is going to be bigger than the time that we had for the blue path. And so therefore,
so there's no reason to think so. It's not going to be a bigger. It's going to achieve the maximum velocity quicker. Therefore, it's going to travel the distance quicker. So this makes no sense. Him to try to imply that this path isn't better than this path. It is better.
We could argue that the blue ramp here is definitely faster than the green ramp.
No, you can't argue that.
Is there a path that gets us from point A?
You can't argue that. The most efficient thing possible would be is if you get all the way to just drop, and then somehow convert all of its downward energy, by just having it flip a lever. Flip a lever, and push something sideways at the same velocity it's going. So you put a little lever at the bottom, it pushes it. That would be even faster. So, all you're trying to do is travel the length of the table at the highest velocity. And it's always the more distance of the table you can travel at the higher velocity, the better. And friction is so minimal that you can't use that as an argument in this case. It really isn't an argument. That's why they all landed at the same location pretty much, is because in spite of the fact that some had a lot more friction, it didn't make any difference.
To point B in the shortest amounts of time there is. But that's the subject of another video, so stay tuned for that. Well, I hope that's helped you understand.
Rubbish, and I don't know what the fuck this is. What is this crap on the screen? What the fuck purpose does it serve? It's like some dancing girl. I can't even tell what the fuck that is. It's a flame or something? I don't know. I don't know what this crookedy line crap is on the shirt. How interesting. Not. Yeah, okay. I just hate the internet. Anyway, alright, so we'll move this up. Fuck. Alright, no seeing to disprove basic experiments. Why hasn't it been done? Okay, did that. I went 3-year electric and 3-year high-powered electric schooling, and that information have come to make sense. True example, this channel, and by your 2-slit explanation, that's pretty simple. So that's pretty simple. I guess I didn't read that very well, but maybe you didn't write it very well. But I appreciate it. Yeah, look, I'm underqualified. It's true. But the fact is that I've done, on the specific subjects I talk about, I'm not underqualified because I have done a lot of research. Alright, too bad they don't do these experiments on the space station. Well, I said that in the day before yesterday's video, of all that wasted time, right? All that time in absolute vacuums and all that kind of crap, and you can do all kinds of experiments, and we don't get to see shit. We see stupid astronauts throwing tennis balls back and forth. Fuck. Trivial, kid science. Chris Hadfield disappoints me as a fellow Canadian. Yeah, we spent a lot of time up there, and yeah, it's all kid science. They don't bother doing anything real. Let's see. E equals Q times V. Q equals coulombs. V equals voltage. So V equals E divided by Q, and KE. Well, so again, this is your own choice. Okay, you want to pretend that's true, then go ahead and pretend it. I'll say you get wrong answers. So until we have somebody prove the actual wattage is what you say it is, it doesn't mean anything. You saying what the speed of an electron is you saying so. Voltage is proportional to kinetic energy, not velocity. Well, fuck you. I'm just going to say fuck you. Prove it. So go ahead and prove it. Show me that you ever need to use any 1/2 mv squared bullshit anywhere, any KE crap. Yeah, no way. All right, anyway. No, it's proportional to velocity. It's not proportional to voltage. No, it's proportional. It's not proportional to voltage. I don't know what that means, but whatever. I don't know half the shit you people type. I don't know exactly what you're saying, but I'm just saying, obviously the electrons are what's providing the energy that moves through the electrical phenomenon. And I think it's just kind of a simple argument that you can understand one electron, okay, can carry different amounts of momentum, wattage, so to speak. And so if it's a high velocity electron, higher voltage, then they don't need to evolve as many atoms. They hit fewer atoms because they hit them with higher pressure. So they do more pressure work per atom, right? Where you could argue that at lower voltages it takes a lot more atoms to lead to the same wattage. So you're evolving a lot more atoms. And that's why you can see the huge correlation between low voltages and high amperages and magnetism. Magnetism doesn't work, okay, at low voltages. At high voltages. If you use high voltage electricity, you're not going to create any useful magnetism. You have to use low voltage electricity because you need the amperage to be as high as possible. So instead of saying you can't use high voltage, I should say you can't use low amperage, okay, because that's the key point. And the key point, what does amperage mean? Amperage means how many atoms did you fuck with. So that's why high amperage burns up wires, is because high amperage, okay, means that you have to use a lot of atoms going slower, less pressure. Okay, but you have to use a lot of them. All of them have to be interested. So they're all moving. So it makes the whole stability of the material weakens because you're using all of the atoms. You're jiggling all of the atoms. So you're making the whole wire messy. Where if you use a high voltage, you're sending a ton of the amperage, the momentum, but you're sending it with just very few atoms being disrupted. So atoms being disrupted a lot versus a lot of atoms being disrupted a little. So it's the same. You can really do pretty good analogies between electrical current and understanding momentum. The voltage and amperage is a real correlation to mass and velocity. Heat is electricity's enemy. Yeah, well, because it disrupts the atoms. But what's the heat being caused by is the key. It's being caused by dirt. Okay? So if you can make something pure enough, if you can clean it of what you would call barriers, places where the atoms aren't stuck to themselves, and there's some other crap in the way, then you don't have a heat problem. Let's see. The resistance of wires is really just their impurity, and that's why if you could do the superconductivity thing, you can make things. What's the right word? You can ensure that everything's stuck to each other. So I think that's what the temperature thing means, is that even if your material isn't pure, when you super cool it, you've essentially made it so nothing can move. Video showing how they measure voltage, which I think is very similar to show objects gain energy from gravity. Voltage, what is it? Well, whatever. I don't know exactly why you're changing the subject, frankly. But regardless, we've already seen Veritasium make a 10 million view video where he tells us what voltage doesn't really exist. It doesn't even travel in the damn wire. It's just a pile of horse shit. So whatever. I'll save that for another day. Video showing how they measure voltage. You can only measure voltage by essentially creating what? Induction? Magnetism? Obviously, so a lot of meters rely on a magnetic effect. which I think is very similar to show objects gain energy from gravity. Well, I don't know how. Who's saying objects don't gain energy from falling in gravity? Who's saying their momentum isn't fucking goddamn increased? Their momentum. God. I mean, you're such a cheater. You gotta paraphrase everything in some kind of cheater way. I'm not claiming there's no energy in gravity. I'm just claiming that it's not a per foot force, retard. I mean, why don't you answer the simple claim? Why is it 9.8 meters per second if you think it's 9.8 meters per foot or meter or whatever? If you think it's per meter, okay, per increment of distance, then why are you saying 9.8 meters per second? Well, I think there's no point in saying which one is first because they're both symptoms of each other, right? So my whole argument is that you're just changing the shape of the atom. So when you change the shape of the atom, you turn into a dipole. So that's why electricity causes atoms to become magnetic. And it just requires you have a material, obviously, that you can do that shape changing by forcing electrons out, so to speak. But you end up creating not just one dipole. They don't get just magnetic this way. They get magnetic this way and this way. So you end up with positives this way and negatives this way. So it's like two norths this way and two south magnets this way. So the magnetism really isn't, it's like a horseshoe magnet, in a way. You've not made a north-south magnet. You've made a dipole. A tripole. I don't know. I guess that wouldn't be right either. But anyway, they all happen at the same time. The voltage, the amperage, the magnetism, everything happens at the same time. So I don't see that as a tricky question in a way. I mean, I'll ask the Virgo guy, did you believe the Veritasium explanation of how current moves through wires? But first to answer, I don't know what that means. Let's see, I remember asking a teacher, which is the first in wire, magnetism or current? I never got an answer. But first to answer. I don't know what that means. Sorry. The world speaks many languages, but not English much. That's interesting, all happening at the same time, yes. Well, I'm just saying it's actually moving through the wire. Look, Maxwell's equations say the current goes this way and the voltage goes that way. I didn't have to think very long before I said, that's not how it works. So even though they said that's how it works, I said, I know that's not how it works. That's a pile of shit. There's nothing going the opposite way. I mean, that's just ridiculous. Oh, the Ringlish, not my first. Yes, I guess I can figure that out now. Yes. It's not my first either. I speak conceptual, yeah. Anyway, I think it was mostly semantics, probably. I'm a bit How can you just say it's mostly semantics? He's basically saying nothing happens in the wire, it all happens in space through induction. That somehow it's all an inductive field that's creating the electricity, and it's not the electrons with momentum pushing on each other. It's some inductive crap flying through space. I mean, come on, it's a huge difference. It's not semantics. I'm a bit distracted, shopping and typing my phone. Okay, well, whatever. It's not my fault. Damn. I didn't tell you to go shopping when I'm making a video. An item with mass can never exceed the speed of light, right? Only photons, they can't either, so I don't know why you're even bringing it up. The elemental force in the universe, there's nothing in the universe that can go faster than the maximum speed of the force that is the universal force. The same force is everything, okay? All the things we call a force are the same stuff, they're just in different patterns. So I'm just saying we have discerned that that stuff moves at the speed of light. And all the other stuff is being pushed by that stuff. So there's no way the other stuff could go faster, because even if I have 1 trillion of them, they're still only going the same speed, and they can only push the same speed they're going. So obviously they can't push something faster than they're going. So nothing's going to go faster ever, okay, than the speed of the force. And it should be called the speed of force. It really shouldn't be called the speed of light, because gravity, magnetism, electricity, everything that is a force and how we understand it moves at that same speed. So I say, duh, that part of this story we all should agree on. That, well, if all the pushers in the universe can only go 300,000 kilometers per second, then, or kilometers, then we're done. That's as fast as anything's going to go, because everything else is getting pushed by that shit. I'm just saying momentum really does work. You just cut it down to the masses of the electrons and the protons, and they're doing their thing. They're getting pushed by this stuff called force. And depending on how the force is arranged, it pushes the electrons more than the protons, or more than the protons than the electrons. So there's nowhere where you're going to show me a photon going faster than the speed of light, right? So this never happens. It's just, it's the speed of light in the material, that kind of bullshit. Yes, things that have a lot of atoms in it means that whatever the light's going through, it's actually going to take longer, because it has to actually hit electrons, and the electrons move slower than the speed of light, and therefore it's going to take a little while for the energy to get through the substance. It's going to slow it down a little. I mean, electricity is rather substantially slower than the speed of light. I mean, we all say it in a way like it's the speed of light, but it really isn't. Because technically most think collide by communication through a field. Technically most think collide by communication. So it's semantic to say the field that is carrying the energy. All right, well, I'm just saying, you can say it's semantics. I'm saying it's a physically different circumstance. Induction is quite different than current moving through a wire. The induction is just a side effect of the wire vibrating. As the wire moves, essentially, the atoms inside of it change positions. It means it's reflecting the universe differently. So I'll go back to my magnet argument. A magnet is not creating energy. It's just reflecting the energy in a polarized manner. So that's why you see it. It's, it's supposed to be purple. And so the force in the universe is purple. And the magnet is sitting there going, I'm just going to reflect blue here and I'm going to reflect red at the bottom. Now, it doesn't do exactly that, but I'm just saying as a simplification, that's all the magnet does. It takes purple and it makes red and blue out of it. So it's taking energy that's hitting it and just reflecting it, segregated. And by segregating, polarizing it, other things that are polarized can see the polarization. So another magnet can see that there's a red side and a blue side, and it has a red side and a blue side, and it's going to switch to force them not to be opposing. But the magnet doesn't exert anything, it just reflects the universe, and a wire is doing the same thing. And when you put electricity through it, you change what the wire is reflecting. So the inductive field isn't taking the energy from the wire, it's just a symptom of the wire having energy pushed through it. But it really, again, this subject is a little bit far from, the kinetic energy subject. It'd be nice if, I know beggars can't be choosers, but it'd be nice if you stayed on the subject now and then. So Tim says, okay, hi Tim, been a while. So the universe is full of the single force. Yes, of two varieties. There's electron force and proton force, but, let's not get too complicated. I want to stick with the ones as much as we can. Because you start going to 2 or 3 and you people get all confused. But yes, there's a single basic force idea, a little quanta of momentum moving the speed of light, and they don't move any other speed, and all they can do is either stick to an electron or bounce off the electron. Those are the two choices. And also electrons and protons, and that's it. Yes. Will there be an explanation for why there are electrons and protons? No. Are they assumed as axioms? They're not assumed as axioms. I'm just telling you that trail is unfollowable. There's no magnifying glass that can reveal that fingerprint. That data is lost, and you're never probably going to find it. Okay, you're not going to find the eggshell that hatched the universe. So, there'll have to be axioms, because I don't think we're ever going to go back in time and watch the universe hatch. Yeah, it's not going to happen. I mean, I can't, it could be that, look, every 10 billion years, I don't know. So you can just say there's some mechanism in the universe. That's why there's something rather than nothing. So there's some accident, some error code, something that happens that poofs universes. Whatever the fuck this is, it evolved into its condition. Okay? So whether you call it error code or a crack or, I don't know what you call it. But the fact is that the idea of nothing is really, okay, nothing. Okay. The idea of something is a problem. So as soon as there's something, you've got to say, well, yeah, you say, where did it come from? But I'm just saying, the answer is going to be something simple. There's going to be an evolution answer. There's not going to be a God answer. There's just going to be an evolution. A computer didn't do it. A God didn't do it. Whatever. Mary Poppins didn't do it. It's not some stupid reason. It's just some mechanical reason that the universe made matter and force. Maybe it just had force in the beginning, and the matter is just, old force that clumps. You can imagine that electrons could be made out of dead force, so to speak. Like two force bits hit each other just perfectly, right on, and then they turn into an electron. Could be something like that. The magnetic force has a push and pull component. Would you agree? Yes, of course, and I've explained why I've done the whole simulation thing. So again, I really have to work on this simulation guide just to get it finished. A little better. It's really quite nice, but it could be a little better. All right, let me see if I can center that better and get rid of this chatty thing. And you can see that better. But I mean, it's all simulated. It's just, there's simple rules. 2 plus 2 plus 2 physics explains the whole goddamn thing. And it's all you need. It's all you need to explain monopoles create dipoles. Dipoles end up creating complex compounds. I mean, it's really that simple. So anyway, back to the comments. Let's see. Do you think that induction takes energy? That's my point, is that the energy is changing the shape of the atoms in the wire. That's using your energy. So your energy is used up doing that. And all the induction stuff is a field effect. It's just the fact that you've changed the wire into a magnet, essentially. You've changed the way it reflects the energy that hits it. All right. So the induction energy is for free. Now the problem is if you're hitting the wire with a weird field, a field with patterns in it, those patterns will disrupt the ability of electricity to travel through the wire. So that's the problem, is the field effect you create can now reflect off another object. So if I put a bunch of coils around a piece of iron, I'm going to cause a bunch of reflections inside, and now I'm going to deter the electricity from being able to change the shape of the atoms, because now I'm disrupting the atoms with the induced field, the field I have trapped. Well, you can disagree all you want. I'm just saying my model works, okay, and it doesn't require anything magical. So go ahead and disagree. Go ahead and choose a model that, in my opinion, doesn't answer the questions, doesn't explain anything. Your physics has no explanation for charge or magnetism. I'm perfectly showing you that a simple idea of an electron force and proton force matching a proton and an electron in terms of behavior. So the electron force travels through the electron and gets converted into an electron force. The electron force passes right through the proton and gets converted into a proton force. That simple trick creates repulsion and attraction exactly like Maxwell would describe. Exactly the right proportions. It creates exactly the charge function. And it's as minimalist as, how, you can't get simpler. I mean, the force is so simple. It just moves the speed of light, okay, and has a color. The function of the electron is I absorb a blue thing hits me, it sticks to me. Okay, if I'm already going against it in direction, then I reflect pieces of energy in both directions. I reflect what I already collected. If I haven't collected any, then it sticks to me and it moves me. And I move some percentage of the speed of light slower. Now I've also explained gravity, because the fact that that electron is now absorbing a force and causing it to move slower means the universe has less energy in it, because I've degraded a force bit. I've taken its speed of light momentum and I've converted it into 1/10 of that. So I've degraded a piece of force in the universe, which is essentially saying I've slowed it down, I've taken energy out of it, momentum out of it. So every time a piece of force goes through a piece of matter and it moves any piece of it, that movement essentially steals a little bit of the force's energy, because it's moving a piece of matter, and therefore less force comes out of the object. So I can use charge to explain gravity, and then I can use charge to explain magnetism. I mean, it all fits and it all works, and it's all made out of almost nothing as moving pieces. There's nothing I had to do that was at all fancy. 5 little rules, and there, proton, electron, proton, electron. Magnets. I'm creating them right in front of you with these simple rules. restart it just for fun. And wind down because we're running out of commenters. But it always does the same thing. Like I say, it'll do it much, it's just there's a couple of little subtle glitches still in it, But you can also understand that every time an electron does actually combine with a proton, connect to it, it releases a bunch of energy, gamma ray, you could argue. I mean, it answers so many questions. It's got to be you can't answer this many questions with this simple a model unless it's damn close to the truth. And such. See, the tricky part is creating a universe, getting everything to be even, so nothing bounces off anything unless it actually hits something and all that, So there's lots of little, the simulation isn't easy, but it's really simple, like I said. And all this source code will be public eventually and all that crap, and you can see how simple it is, the simple rules it's behaving under. And it's just a matter of, creating enough density of force versus the size of the objects, because size matters. So you could just see, the little red one hit the blue one, and a little poof of energy. It gave away its momentum with a little higher frequency emission of force. And such. Anyway, okay, let's see. Change is a hard concept to get my charge is a hard concept to get my head around. Can you give me the charge for dummies explanation? Oh, I think I already have. I mean, I can draw it again and we'll see how that goes. Just for you, Tim. I'll consider you worth the trouble, so I'll bother doing it. Yeah, maybe if I just make this like that. Alright, the rule is so simple that, I mean, frankly, it's just so damn simple. I almost shouldn't have to go over and over this. So the simple idea is we know we have two objects, electron and proton. Okay, so I'll make the electron red and the proton brown. Now we know the charge they have is the same, so I would argue they have to have the same size, physical size. But yes, this weighs more. The proton is heavier for whatever reason. It interacts slower. All right, and the simple rule is, okay, say there's two kinds of force in the universe that match these two colored objects, okay? So you have electron force and proton force. And that's it. And they all move the speed of light, and they all have a vector, and they only move in straight lines, and blah, blah, blah. But they can't interact with each other. They only interact by the conduit of the matter bit. Because if they interact with each other, they just exchange velocities and nothing ever happens, blah, blah, blah. Anyway. All right. So when a little brown force hits a red, it just goes through and it comes out red. All right, so now you can sort of understand. Well, okay, now we'll do the red force. So if the red force hits, it's a little more complicated, right? So if the object isn't already moving in an opposing direction, so if there's no opposing force, then this one sticks and moves the object in this direction. If, on the other hand, okay, I will just remove that arrow. This one was already going this way. It already had one stuck this way. Then when this one hits, these two arrows can now do what they want to do, which is just reflect off each other. So when this one hits, this one reflects, and this one reflects, and this stops moving. So that's how motion is acquired. So when more things hit you from this side, you start catching more and more up little force bits. This starts going faster and faster. So it starts off the 10th of the speed of light, then it's a 20th of the speed of light, and then a 30th of the speed of light. It goes faster and faster the more force it collects. And obviously now it takes more impacts to reflect that energy, but obviously it's going to crash into a lot of little red things. All right. So that's the simple, those are the simple rules. So it sticks when there's no opposing energy in that direction, or it reflects when there is opposing energy. So if there is opposing energy, then it reflects the energy. And yes, it could be a reflection this way, you know, because it's got a vector in the opposing direction. So the idea is what happens to these two objects, okay, put very simply, okay, let me put another electron here. Obviously everything here, all the brown either sticks or it reflects. So it's always just reflecting browns, mostly. And all the reds get converted into browns. So all this does is always reflect brown. And this, because of the same inverse rule, is always reflecting reds. Okay, so it's just like Maxwell's drawing of force lines. Okay, lines of force. That's exactly what you have. You have an electron has the opposite to the proton, so they can get close to each other because neither one of these, if the red hits this, it just goes straight through and comes out brown. If the brown force hits this, it just goes straight through and turns red. So there's no pressure between them. But if I put another electron here, oh, you can see how big problem, right? Because everything, all the brown force is being converted into reds, and all the browns here are being converted into reds. So it's adding extra red going this way, and extra red going this way, plus just the reds that are already there reflecting. So every time they get any kind of close to each other, they're constantly hitting each other with red force, saying go this way, go this way, go this way, go this way, go this way. They're pushing each other away. And that's charge. Done. For dummies. Obviously, you know, obviously that's too complicated for, you know, whatever 80% of the humans on Earth. But I'm assuming you're a little better than 80%. If the sun had a massive solar flare, it would take 30 minutes. We already know this. Before NASA found out it was coming. 30 minutes? I don't even know what you're talking about. I mean, that doesn't even make any sense. It takes 8 minutes. So you're saying the solar flare, you're talking about an electron, what do they call it? Plasma. So you're saying it would take 30 minutes for the plasma to get to us. Yes, because the electrons, the matter, takes longer to get here. So you can only get it up to a certain amount of speed. Okay, a plasma will move fast, but it can't move the speed of light. And so just depends on how dense the plasma is, how much energy it takes to move it, and how fast it can be moved. But yes, you can move a plasma fast, but it's still some. I mean, 30 minutes implies that it's you know, that would be 30 minutes would be 1/4 of the speed of light. So is charge the property that a red object will interact? Oh, I don't know. I know. I just explained how it creates polarity. It's obvious. I guess, okay. So charge is the property that the red object will interact with red forces and ignore, but change brown forces into red force. Yes. I mean, they're two different properties that cause the same effect. I can do it without the conversion, right? Without changing the color, it still works. It's just that if you change the color, it works even better. So that's why the color change is there, is because it just works so much better with the color change. So we're just trying to approximate, you know, and get it to do match. So I'm just saying, obviously the force differential between electrons and protons is greatly enhanced if I can make the electron exude nothing but brown, reflect nothing but, and then make the electron nothing but red. If I can make that happen, okay, then they're going to match Maxwell's drawings more explicitly. The dirtier it is, well then yes, the less it matches. You want it to match the inverse square law. You want it to match a light bulb. You want it to match in terms of how it dissipates and how it creates this, how it creates the strong force, essentially. How it creates this incredibly strong force repelling protons from protons and repelling electrons from electrons. And you strengthen the force by doing that color conversion. By doing that simple force conversion, you multiply many times over how much things repel. So I mean, it's really 2 plus 2 plus 3 physics, right? Because there's really 3 kinds of action: reflection, absorption, and conversion. But it doesn't sound as good to go, 2 plus 2 plus 3. But anyway, okay, if I have to. Okay, so I guess we can go back to undrawing board. And 2-minute warning or whatever. "40-second warning," something, some kind of warning. I mean, frankly, you don't have to understand that I have a perfectly good model of charge to understand that mv squared is crap. So we really should do the one subject at a time. I think it's an axiom, but do you have a hypothesis for how a red object changes the brown force into a red force? Well, the hypothesis would have to do with something to do with, again, you'd have to just make up some idea of how these things originally got created and all that kind of shit. And so what they really are, what is an electron and what is a proton. And so if I speculate that they're made up of force hitting each other, then I can speculate that the force has to hit each other in 3 different dimensions. So you end up with an object that has a shape, okay? It's a hexagon or something. And and so in the case of the proton, the reds are all on the outside or something, and in the case of the electron, the reds are all on the outside, inside. And so the change comes in, and the force comes in, and it ejects a piece, that's the opposite color, because that's what the last thing it hits is inside the object. So whatever the exterior is made out of is what the thing ejects. Something like that. And obviously over time, okay, somehow it has to remake that membrane, so to speak. The membrane has to stay red for it to keep producing red as an output. And so there's some other mechanism that, reinstalls the red bits, blah, blah, blah. So yeah, it's a worthy question in the sense that there's obviously a mechanics to it, but I'd say for the purpose of understanding magnetism and electricity and charge and gravity, you don't need all of that. Oh, whatever. Spin is just horseshit. There's no spin in the elemental universe. Let's see. Trying to say a proton is just an electron in a reverse spin. Well, I don't even know what that's a sentence to. What do you? If the sun had a massive solar flare, I can't even connect your comments. Trying to say a proton is just an electron in a reverse spin. Fucking hey. I'm sorry, spinning electrons and protons? I mean, we know these things are so consistent in their behavior. how can you have wacky electrons and still have a theory that makes any sense? Because electrons are so consistent in their behavior. They can't possibly have a spin property. Do people even understand the scientific method? It seems like the opposing sides can't even understand that one. Well, they don't understand evidence, okay? So that's the big word, evidence. You should have fucking evidence to support a theory. And your model should be simple, not complicated. I mean, Occam's razor, you're really not, the elemental universe shouldn't be more complicated than, our universe. If there's ESP, the electrons shouldn't have it. We should have it. Whatever vibrations means. I mean, it's got to be cause and effect, okay? So if something's vibrating, it's got to be in an energetic field that's causing it to vibrate. It's an emergent property. It's not an elemental property. Nothing's elementally vibrating. I mean, clearly, electrons and protons do a lot of actions in a millisecond. A billionth of a second, they have a very active life. So yeah, they're doing lots of things, okay? But whatever they're doing it because it's being caused. They're not doing it because that's what they do. They just sit around and vibrate all day. They don't do that. They are forced to do it. Forced. Matter is forced to do anything it does. Anything an electron or proton does, it does it because it was forced to. A force forced it. Well, anyway, it's a reasonable experiment. Did a later video. Let's see how many viewers there were. See what we can glean from this experiment, like all the others. Let's see what we got here. 11. So not much better. So let's. What I learned is that it doesn't matter. Early in the morning, late in the afternoon, not much better. Alright, should light travel faster than matter? Well, of course it does. Should the things that are pushing go faster than the thing it's pushing? Yeah, that's the way it should work. Shouldn't light travel faster through matter? Why would it travel faster through matter? So that's just absolute insane crap. The matter is big stuff moving slow. The force is little stuff moving fast. How would you go faster if you bang into a bunch of shit? So if I put a bunch of crap in your house hallway that you have to kick through, are you going to go faster? No. They play games with words. I mean, they're constantly always lying about stuff, and it's just a lie when they say, oh, we have light going faster than the speed of force, faster than the speed of light or something. And it's the speed of light in the substance. So every substance, okay, you can figure out that thicker things are going to slow the light down more than fast, thin things. The more atoms the light has to hit, the more lenses it goes through, the slower it's going to be going, because frankly it has to hit atoms. Hitting atoms absorbs time. Well, whatever. I wouldn't use the word in. The force bit sticks. Whether you want to say it's in, fine, I don't care. But yes, it spends time pushing the electron or the proton. It slows it down. The force can't keep going the speed of force when it hits the electron. The electron's big mass. It has to spread the velocity over the bigger mass, just like in regular kinetics. So it hits, it's got to push the big mass, so it goes much slower. So the force isn't getting where it would have gone if it wasn't pushing this slow thing in the way. Force can only be in two conditions in the universe. It's either stuck pushing a piece of an electron or proton, or it's freely flying. It's only two places it can be. It's only in two conditions: pushing or freely flying. That's it. I just forgot until last week that newtons is 1 kilogram meters squared. You know, who cares about any of that crap, right? I mean, you should be able to understand a newton as just being a weight. So it's 100 grams. That's a newton. 100 grams. I don't need kilometer, meters, second squared crap, do I? No. I mean, how does that make any sense? 100 grams equals 1 kilogram meter squared. That makes sense to you? It doesn't make any sense to me. It just doesn't even make any sense, right? I mean, meter squared. There's something wrong with what you wrote there, but that doesn't even make any sense. 1 kilogram and then a meter square meter? What the fuck is that? Obviously a newton isn't a newton, okay? Newton didn't bother with newtons. So let's understand it's a contrivance that they did to Newton, okay? Newton just cared about weight, okay? He said, how much does it weigh? He didn't bother with this crap. I mean, the fact is a newton equals 100 grams, okay? I'm just saying, that's what it equals. And 1 kilogram equals 1 kilogram, which is 10 of those units, 10 newtons. Why make it any more complicated than that? If I just went through the rest of my life and I said a newton was 100 grams, and I said a kilogram was 10 newtons, wouldn't I have all that I need to know? What else do I need? I mean, it's all the reference you need. You can compare the scale. You can put everything on a scale and just do the comparisons. I don't need Newton, Joule, all that. I can just measure it on a scale. I don't have to make it any more complicated than that. I can convert everything into a pressure and just say how much pressure can it apply. F equals ma. Well, it's not Newton's formula, but anyway. So KEM squared is a Newton. Yeah, whatever. Just keep doing the same thing. I'll just keep saying I don't need to make it that complicated, Tim. Is a Newton 100 grams, the weight of 100 grams? Is that a fact or not a fact, fuckhead? And is a joule 10 newtons? Because it's actually a 1 kilogram, the weight of 1 kilogram. Is that or is that not true? And if you drop the 100 grams in gravity, you'll end up with... yeah, I gotta be careful. A half of a joule. Something like that. P equals mv equals kg. Whatever. Totally uninteresting. There's no evidence of this, whatever you're drawing there, right? I mean, it's okay, so it's mass in kilograms times meter second, whatever a meter second is. I mean, I can just put it in seconds. I don't need, what do I need this crap for? I put the velocity in seconds. Why would I do meter seconds? Why would I bother with that crap? Just explain to me, okay? It's mv. Velocity is just a number, velocity. 60 miles an hour, 60 whatever. So it's just a unit. So you're just saying it's seconds, okay, that you're deciding that what the velocity is in. Well, I guess the meters is, just as important as miles per hour. Fine, whatever. There's no argument. What are you arguing exactly? Who is opposing that? It's when you square the seconds that the problem shows up. I have no obligation to say per second, or square the seconds. I don't want to re-argue this, frankly. If that's what you want to do, then fuck off. I'll put you in a timeout or something. We've been over this 4 million times. I have no obligation to think there's any reason that acceleration is squared velocity. Somehow an acceleration is a squared velocity, where velocity isn't squared. Velocity sucks. Acceleration is super powerful. Velocity, weak. Fuck you. I just don't, the games people play. It all comes down to, look, energy equals weight equals pressure equals, what's all the other, heat equals, all of it is energy. All of it is the same fucking thing. It's a mass moving a velocity. That's all energy ever is you go find something and you say, how much does it weigh and how fast is it going? What's so complicated, fuckers? People are hopeless. If we describe a car at a constant speed, whatever, we would say units of length over time. Fine. What units should we use to describe acceleration? Length over time. It's just a change in your velocity. Why would it be in why would it be in squared units? It's nonsensical. The velocity is happening every second. We don't say 60 miles an hour per hour. We don't do that. There's no reason to square the seconds. There's no reason to square the rate of acceleration. 9.8 meters per second. That's all you need. You don't do 9.8 meters times 9.8 meters. You don't square 9.8. That doesn't tell you anything. You find out how many exact seconds you fell in the gravity, and then you do 9.8 times how many seconds. There's no squared involved anywhere. And acceleration's the same thing. You're accelerating at a rate. You multiply the rate times the number of times you did the rate. What's so complicated? Where's there any need to square anything? Oh, but really, we've done this so many times. Alright, they repeating what they have read and not done the hard work explaining where and how to use these concepts. Well, yeah, they haven't done any of it. They've researched the history, and you'll see the whole thing is just made up crap. For 150 years, they just had mv squared. They didn't have any half in it. So they're getting these insanely stupid numbers that were way off, a half off. 100% off, essentially. And they thought everything was just fine. So, it's obviously not very credible physics when you can change a formula by 1/2 and they didn't barely notice the difference. What credibility can you say? One day they said it has 300 joules of energy, the next day they said it's 150. that's credible physics? Well, I wish I knew what happened in 2014. I guess that wasn't LIGO. Yeah, but whatever. Ugh, God, the world is just... I just wish that people would even try to figure out the geometry of squaring a velocity. Like, where could it ever make sense to square a velocity? I mean, how could you ever, like a velocity cubed, where that would ever be relevant? How could that ever be a reasonable thing to do? And the only time it could ever work in mathematics is because you kind of did your switching of things around and you end up putting the square on two numbers that are going to get multiplied anyway. And the square really should be on the m, but you put it on the v instead, and it doesn't matter because you're going to multiply them times each other anyway. But I just mean, what would a square velocity even be as a concept? How can you have a volume of velocity? You know, I mean, it doesn't make any sense. Now you could say you could have a volume of acceleration, but the volume would be not a squared function. It would be based on how many units of acceleration, how many seconds. I just, you know, people just, you should be saying, boy, I sure wish our physicists had enough credibility to do that, show me it taking 4 times the fuel to go twice as fast thing. I sure wish they would actually do that experiment somewhere. They can't even say that. I should describe that as a distance. Well, again, you can't describe it as a distance because the only way you can describe it as a distance in space, the distance is obvious. Something going twice as fast goes twice as far. So the only way when you're collecting the energy in friction, I've already explained how that's not fair. So what does distance have to do with it? The way you measure a velocity isn't the velocity, okay? I mean, it's just not. Okay, the fact that you're measuring it in this complex, indirect way isn't a velocity. Okay, so, and again, the velocity is always in the form of a rate. You can't square the rate. Why would I square the rate? I have to square the rate times a number. I have to multiply the rate times how often the rate happened. What sense does it make to square the rate? Again, distance is, it has to be understood that the distance is a cheat. Unless you're doing its actual, you know, like I said, in a frictionless environment, it's velocity. If you're going to let friction decide what the rate of its acceleration is, then you're understanding again that gravity is controlling the rate at which friction is taking the energy. So that's bullshit. But I'm just saying, yes, the fact is you measure the rate by saying how far does it travel in this amount of time, and I take the smallest unit possible. And so what do those tiny distances have to do with squaring seconds? Squaring a velocity is like squaring how you're going in a car. It just isn't accurate and incorrect. They're squaring the acceleration, but regardless, squaring a speed that is a rate, there's no reason to square a rate. You multiply the rate times how often it happened. VF equals VT, VT, blah, blah, blah. Who cares? I mean, just keep doing this shit. MGH, MGH. Do you think that gives you a right answer? Twice the time, twice the weight, twice the velocity, 4 times the distance. And that's all you see. You say it's about 4 times the distance. I say it's about twice the time. It's about twice the weight. It's about only twice the velocity. And your counter argument is just to belligerently spout the same crap over and over and over again, that somehow 4 units of height equals 4 units of energy, when gravity is overtly telling you, screaming at you, no, it's only 2 units of fucking time, moron. It's only 2 units of 9.8. Not 4 units of 9.8. 2 units of 9.8. If I take the fraction 1/3 and divide by 3, I get 1/3 square. I don't care. I'm totally uninterested. If you think squaring, elements of fractions make sense, then forget it. We have nothing to say to each other. I mean, I know that 1/3 times 3 is, 1. That's what I know. Shit. It's a real number. I don't square things. Squaring things is retarded. I'm just saying, squaring non-geometrically squarable objects is stupid. Acceleration needs to be, and I'm just not going to keep doing this VO and VF. V final versus V initial divided by time. And I wouldn't argue with that. That's the rate of your acceleration. Why would I square the rate of your acceleration? I can ask it again. Why would I square that number? Respectfully, Merker, what is your source of info? Education. 1/3 divided by 3. Oh, well, who cares? So 1/3 of a third is, in my opinion, okay, 1/3 of a third would be a sixth. All right. 0 in acceleration. AHA Oki. I don't know what that means. A high Ogi? I don't know. Maybe it says. I don't know. I don't know where he gets that. What he's doing there. Don't know what that could possibly mean. Again, this all comes down to the simple mistake Leibniz made, and you're just going to keep making it. Galileo saw it. Descartes saw it. Newton saw it. They all saw that gravity is fucking with you. Okay, that's all. It's just fucking with you. It's just playing a game, okay? Yeah, 4 times the height doesn't mean 4 units of energy, because the energy is being acquired in a unit of time. The paint sprayer does not get the same amount of paint on you. If you go faster through the paint spray, you get less paint on you. Okay, same distance. The faster you go, less paint. Gravity's doing the same damn thing, and you're falling for it. You're a sucker to think there's something other than how much time are you collecting the force without losing it to the ground. So you're not touching the ground, therefore you're free falling in the gravity. You can collect the force, and you collect it at a rate of 9.8 meters per second, or whatever, 2.6 meters per millisecond, or half second or a quarter second. There's a rate. You're collecting it at that rate. Okay, you don't square the rate. It's retarded. Yeah, I don't really care. I don't do much of this squaring fractions or multiplying fractions or doing all that crap, so I really don't care what your arithmetic says. I say 1/3 of 1/3 is 1/6. Okay, that's what I say. Or 1/9, right? I probably said something wrong. 1/3 of a third. So if you have 1/3 of something, I say how much is it? Yeah, it's 1/6, right? 1/3 of a third. No, it'd be 1/9. Okay, I'm sorry. But who cares? How does this get to the conceptual truth? The rate is 9.8 meters per second. You're saying I should measure the rate based on how long it traveled, how far it traveled. That's stupid. I mean, yeah. So I've stated this so many times, but look, my bucket analogy, okay, collecting rain in a bucket is my analogy for gravity, and I'm saying it works perfectly. All right, and all I'm saying to you people is your analogy that it has something to do with, I don't know, how much I move around in the rain, something, I don't know, distance I travel in the rain, something distance makes all the difference, when no, it doesn't make any difference at all. It's just how long are you in the gravity. It doesn't matter whether you're going up or down or sideways. It doesn't matter which way you're going. It just matters how long you're in the rain. That's how you collect it. And as soon as something stops you from falling in gravity, it's going to stop you from collecting velocity. Well, how completely it stops you. Obviously, if it doesn't stop you from falling, but just slows you down, then obviously you'll collect less and less per second from the gravity. But really, that's the subject I gotta keep focusing on, I guess. This is what started it all. I mean, the simple truth that the 4 times the height thing was always a wrong way to understand gravity. It's not about how high you go up in the gravity. It's about how long you're in the gravity. And that simple thing is the whole reason this stupid formula exists. It wouldn't exist if it wasn't for that quirk of reality, that as you acquire a velocity and you go faster and faster, you end up defeating the very force that's trying to make you go faster, in a sense, because you're speeding through the distances. The last mile a meteor travels, it gets nothing from gravity. I mean, the amount of speed it gets from gravity is minuscule, compared to its speed it's already acquired, because it's rushing through the gravity so quickly. I mean, if it wasn't for the atmosphere, so go to the moon and watch an asteroid hit the moon's surface, and you'll see that the moon's gravity didn't have much to do with it. Alright, well, I guess that's all there is for today. And such. They want to discuss mathematics. Yeah. When the whole point is that mathematics is clearly broken. Per second does not mean second squared. These concepts are confusing. Metrics, I don't even know what that would mean. Joules, watts, kelvins, well, you don't have to bother with that, and so on. Yeah, well, I'm just saying, we already know that a joule is a watt, so those two things fit together quite nicely. And the tricky part is the Newton being 1/10 of a joule. But it only it gets more complicated, because you have to realize that when you drop something, even though it's going 9.8 meters per second, when it reaches the distance, it only travels half the distance. It only goes 5 meters. So that makes all this a little bit more confusing. So yes, there are confusing bits, but I'm just saying, I don't know if the watts and joules are really the problem. I just say fuck joules altogether and just stick with watts, because watts are real. Okay, we all familiar with watts. We can all bang 2 wires together and see the bigger watt spark. We can all know the difference between a 50-watt light bulb and a 100-watt light bulb. We can relate to a watt. Can't relate to the stupid joule-y thing. I mean, it's the impact velocity of a stick of butter dropped 1 meter. So a stick of butter, 100 grams, falling 1 meter, weighs a joule. A kilogram is really the weight of 2 joules, I think it is, right? Kilogram is the weight of 2 joules, 2 point something joules. So that's the tricky part, the part that's broken. yeah, that's really broken. is that 100 grams dropped 1 meter doesn't weigh a kilogram. It weighs a watt. Yeah. All right. Oh, here he just keeps going. Sometimes you are incredibly uninteresting, Tim. The 1/3 divided by 3, if you replace the 3 with the variable seconds, you get 1 divided by second squared. Well, I'm saying, you're just going to keep doing this crap. So yes, you put a fake unit under a fraction. Why? Why did you put a fake unit? You're supposed to just put a 1 under the fraction. You're not supposed to put a 1 second. You're just supposed to put a 1 under it. Not a 1 anything. It's not supposed to be a unit of anything. When you convert a number into a fraction, okay, you're supposed to just put a 1. Not 1 second. 1. It's 1 unit, period. That's all you're saying. It's this thing divided by itself. It's a 1. Not a 1 second. A 1. Oh, fuck. A watt is derived from energy. No, it's made up exactly to match the joule. So don't tell me what it was. I read about where these units were invented. So fuck you in the ass until dead. No, nothing was derived. Liar. You know. They were deliberately contrived to equal each other. Alright, so that's probably a good enough note to end on. What a pile of shit. That any of this derived crap has anything to do with deriving anything. Like they invented this out of pure science. They didn't invent any of this science out of pure science. They invented it out of their own axioms and their own horse shit. Alright, so till the next time and such and so forth and whatnot. I give you a low rating, participants. There's only 8 of you. Yeah, it's just a suck parade, frankly. So anyway, but it does demonstrate that the American audience is lame. Yeah, maybe that's what it demonstrates. Because yeah, they can't show up and make an argument. Anyway, till the next time, it's whatever, blah blah blah. Just what is the point? I must say, even smart people can't pay attention.